All right, so what I'm going to do now is we'll start talking about diffuse gray surface radiation exchange. So we're going to be talking about surfaces that look like this one up here. Let's develop a model for that. And then eventually, I think in the last lecture, maybe even Wednesday, we'll be able to talk through semi-gray a little bit. OK, so diffuse gray surface radiation exchange. So we're now looking at multiple surfaces that see each other that have differing emissivities as a function of each surface. But we're assuming those emissivities for a given surface are constant. So things we need to think about. Let's draw a surface here. I've got my surface here. We can imagine it extends this way sort of infinitely. When we're talking about the radiation exchange, we need to account for all the different ways that light can come to a surface or leave a surface. So what first would happen is, let's say we have light coming in. We'll call that light G. So the symbol G stands for irradiation. So G is irradiation, as opposed to radiation. Right? Irradiation is all the light that is incident on a surface. Radiation is what happens when you have a decay of an electron from one to another, right? Or some kind of a splitting of an atom or something like that. So irradiation is what's coming into to strike the surface. Once that happens, I guess you can have a few things occur. First, you could have light that's reflected off. So that reflection would be characterized by what we're going to call rho, which is the reflectivity times that irradiation. Let's see, make a note of what these things are. So first I've got rho is reflectivity. Okay, again, we're talking about diffuse hemispherical properties here. So reflectivity, and then the other thing that could happen, or one other thing that could happen, is light comes in is actually like absorbed. It's absorbed by that surface. So that would be characterized by the absorptivity, alpha times G. So alpha is our absorptivity. That's actually not everything that can happen, right? If you are a piece of glass, you understand why. Light can pass through, right? You can actually have transmitted light. So we have to account for that as well. You have light that comes through, probably is refracted, and then passes through. So that would be what we'll call tau times G, where tau is the transmissivity. OK, so all these are the possibilities of what could happen. They all have to add up to 1, right? You can't. The energy that's coming in has to be split among these things. That you can't, invent energy out of this. So you could do an energy balance on it and figure out basically that the reflectivity plus the absorptivity plus the transmissivity has to equal 1. All right. You could go back and swap out like absorptivity for emissivity here if you wanted to, because they should be equal, at least in the case of a diffuse gray surface. But these all have to add up to 1. Furthermore, I guess if you know it's an opaque surface where tau is equal to 0, then of course rho plus alpha equals 1. So in most like opaque surface situations, there's a direct relationship between reflectivity and absorptivity, and they're complementary and have to equal 1. Okay. So those are all the sort of mechanisms. Now when it comes to modeling this, when we're looking at, say, let's say we had a two-surface problem here. You have some light that's coming in from, I don't know, like a light source, the sun, let's say. You have light that's coming in from an external light source. You have light that's reflected off and that goes to another surface. Let's say there's another surface like up here. Maybe we could even draw it. So you have another surface that's like sitting up here like this. So it also has light coming in, and that light coming into that surface could be absorbed, reflected, transmitted. Let's say some of that's reflected. That's reflected, and some of that's going to hit this surface. So we have now in our irradiation, we have to account for the fact that everything from every surface, every source is coming in, we have to account for that in that term G. And we have to account for the fact that our surface, the one we're concerned with now, could be doing the same thing to other surfaces. So it's not just the matter of balancing, t to the fourth powers in an equation. It's balancing that emitted part, but also what's reflected or coming in from other light sources. So let's maybe sketch this a little bit more carefully and then have some terminology. So we have down here our surface. We have incoming our irradiation G. Let's call that G on surface I. Okay, we have reflected from the surface. We have rho times GI. We also have potentially emitted from the surface in any particular direction. Epsilon I times EBI, or just EI, right? So epsilon I times EBI. So we're really concerned with what is this total that's leaving the surface. That's what we need to know. So this here, let's call these two things are called radiosity. And we typically assign to radiosity the nomenclature J, so capital J, I. Yeah.
When you say I, are we assuming a node on a surface, or are we assuming like length?
For this, we are assuming I refers to the entire surface. So it's surface I. And yeah, that's an important point. I mean, maybe later on you'd decide that if I had this situation up here, I care a lot more about capturing what's happening in the corner than I do way far away. For now, we kind of assume these are like a differential surface, or it's a surface where the view factor from this surface to the other surface is uniform across the surface. So we're essentially modeling this entire surface as a single temperature with a single EB at the temperature that it's at, and then that corresponds to a radiosity J. Okay. So radiosity, I guess we can come up with some relationships there. So radiosity is, we'll call Ji is equal to the reflected light rho I times Gi, the irradiance, plus emitted emissivity times EBI. The energy balance on the surface itself says, all right, Q dot at I, that's the radiation, the net radiation from the surface, like there'd be what's either absorbed or emitted. That has to be related to these things. And that's going to be equal to the area, AI, times the radiosity, Ji, minus the incident irradiation, Gi. And that makes sense, right? Because you're saying if there's a heat flux, a net heat flux across the surface, it's going to be equal to the area of the surface, times what's total leaving minus what we know is coming in. So that has to be coming from the surface. So that's our net, maybe say net heat transfer for surface I. Anything else here? Okay, so that covers, I think, the definition of radiosity. Next, we can go through and think about how to actually use this in a system of equations. So we'll do that on the next slide here. Okay, so let me just rewrite a couple of things. I should have done that before, but we have two equations that we can use. So we have our radiosity equation, Ji. So Ji was equal to rho. Let's assume this is an opaque surface. And then for rho, it would be 1 minus alpha, which is the same as 1 minus emissivity I, times Gi, right? So that is our amount that is being reflected, plus what is being emitted, which would be epsilon I EB I. We had that equation, so let's call this equation 1. We have this equation here, Q dot I equals AI JI minus GI. Let's call that equation 2. So I can take equation 1 and solve this for GI. That gives GI is equal to JI minus epsilon I EBI divided by 1 minus epsilon I. So I could take that, and let's sub that equation in over here to equation 2, where that GI appears. What we are left with then is Q dot I is equal to AI times the quantity JI minus the fraction JI minus epsilon I EBI divided by 1 minus epsilon I. We can kind of pull things apart a little, so let's get the JI out of there. That looks like this. It would be AI times JI times 1 minus epsilon I divided by 1 minus epsilon I. It just comes from pulling the JI out of that second term. Then minus JI minus epsilon I EB I over 1 minus epsilon I. Okay? Almost there. So the last thing we can do is say this Q dot I is equal to AI times minus epsilon I JI plus epsilon I EBI divided by 1 minus epsilon I. Finally, last step. Okay. So this is maybe all that work to get to this point, which is to say Q dot I equals epsilon I AI over 1 minus epsilon I times EB I minus JI. Okay, so I did all that trouble, one, to convince you that there's a geometric relationship here. There's a sort of energy balance and geometric relationship that gets us to this. Or by geometric, I mean surface. There's a surface relationship that gets us to this. This is saying now I've got a heat flow. I have a potential. The potential is my black body emissive power minus the actual power that's leaving the surface, the radiosity. It's like a temperature potential, and we got something multiplying it. So again, we have what looks like a resistance formula. Okay. This resistance formula effectively is saying R, let's call this RS for the surface resistance. RS is equal to 1 minus epsilon I over epsilon I AI. And then, of course, Q dot is just the potential divided by the resistance. This surface resistance characterizes how difficult it is for energy to get past the imperfect or non-black body boundary of the surface. So you can actually model a surface by saying, okay, I know how much is leaving. I have what's effectively a power output here. I know what the temperature of the surface is. The temperature corresponds to the actual measured temperature of your surface, sigma t to the fourth. That's my black body emissive power. Then there's an impedance that prevents me from getting all of that black body power out into the radiosity. So that's sort of what this resistance is telling you. So now we have our, again on this, the units are 1 over meters squared. Okay, so we have 3 maybe classifications of resistances now. One that has to do with Fourier's law, and 2 that have to do with radiation. The first in the radiation is our geometric resistance. That's how hard it is to get from a surface through space to another surface. The surface resistance has to do with how hard it is to get from my black body power to the actual emitted power. Right? And it's purely a function of emissivity of that surface.